Okay, let's take a look at the next set of slides from section 4.8 on other discrete distributions, random variable distributions. And the next one we're going to take a look at is the negative binomial distribution. So this is just an adjustment on the geometric distribution. So let's just adjust the game that we played as a contextualization of the geometric distribution so that it fits the negative binomial distribution. So the game was you use a cup, you roll a fair six-sided die without revealing the result. Your partner tries to guess the result. And the question is going to now be shifted to how many rounds will be played on average if the last round played is your partner's third successful guess. So in this sense, what's happening is we're actually accumulating successes instead of waiting for the first one. We're going to ask, well, how long do we have to play until we get three guesses that are correct? So intuition would stand to reason that this is going to have a longer expected value than the previous result in the geometric setting. And let's go ahead and see if we can get a sense of what's going on using some theory. So here we go. Okay, well, let's go ahead and start by defining a random variable, y, and we'll let that random variable be equal to number of rounds played until three successful guesses. Okay, so that's sort of what's going on there. We've got to think a little bit about what values can y take on. Now, if we're waiting until we have three successful guesses, it should make sense to you that the minimum value for y is 3. But of course, we could play for quite a while until we accumulate enough guesses, accumulate enough rounds of play to successfully to accumulate 3 successful guesses. But definitely the first possible outcome is y equal to 3. So let's find the probability that y is equal to 3. Well, it should make sense to you that that's just equal to 1/6 raised to the third. It's a fairly unlikely outcome because, of course, getting 3 successful dice roll guesses is pretty unlikely. 1 out of 216, if I'm not mistaken, is the probability we get the first 3 guesses, successfully guess it on the first 3, I guess, rolls. But it gets more interesting if we start talking about, well, what about y equals 4? Okay, so let's just kind of come over here to the side and think to ourselves, okay, if you have 4 rounds of play that accumulate 3 successful guesses, then that can happen, a couple of different ways. I mean, we could have 2 successful guesses right off the bat, a non-successful, and then end in 4 rounds of play with the third successful guess occurring on the 4th round. Of course, we could have in this sort of setting, success, non-success, and then 2 successes in a row. Or we could start out with a non-success and then have 3 successes in a row. Now, the thing that should sort of make sense to you is that the end here has to always be an S, and because of that, there's only one way that last piece could, I guess the last round of play has to end on a success. The interesting thing is here in the intermediate rounds of play, we have 3 different ways, I guess, that the 3 rounds of play can occur. And I guess the way that I would think about this is that, what we're doing is we're just replacing the 2 successes, let's circle them up, in all their possible positions in the 3 rounds of play. So, one way to think of this is this is equal to 3 different ways where I guess, if we were to use combinatorics, we have 3 locations in which we're putting 2 successful guesses. So it's 3 choose 2 ways that we can have the first 3 rolls be 2 successes and a non-success, and only one way that last roll can be a success. So I guess where I'm heading for here is that there are 3 choose 2 ways to arrange the first 3 guesses, and then each one of these is going to be a sequence of 3 successes and 1 non-success, so it looks like that would be 5, 6 times 1 6 to the third. Let's take a look at the probability that y is equal to 5 then. Okay, so now we've got 4. Let's see, let's just kind of think about it here. We could get the two successful rolls right off the bat, and then if there's going to be 5 rounds of play, we must have 2 non-successes followed by a success. The question is, how many different ways can that occur? And it's the same as above, that this last one has to always be an S, so I'll put an S, I guess, down here, and it's rearranging these 4 that yields the different outcomes or possible outcomes. So we could have SN, SN, we could have N, S, S, N, S, and that's the only way that N could be in the 4th position. So let's do S, N, N, S, S, let's see, N, S, N, S, S, and then we could get non-successes followed by 3 successes. And again, it should make sense to you that what we're really counting here are these 4 positions, and what we're placing in them, in similar to above, is 2 successes in those 4 positions, and we're counting all the different ways that we can choose 2 locations for the S's from 4 locations. So in this case, it's 4 choose 2, or 6 ways to choose those first 4 places, and of course 1 way to choose that last place. So it looks like this is 4 choose 2 places to put the successes. We've got 5, 6 raised to the second because there are 2 non-successes or failures, as followed by or along with 3 successes, so 1 6 to the third. And so it kind of stands to reason that we've got this knocked out. If you sort of look at the way this generalizes backwards, that would be a 0, 1, 2, 3, and this would be, let's see, it would be 2 choose 2, right? That's 1. So 1 times 1 times 1, 6 to the third. It seems like the generalization now holds that we would have y equal little y is always going to be, let's see, so this is always y minus 1 because we're arranging, you know, everything but that last success. So on top we have y minus 1, and on bottom we always have, well, 2 less than the number of successes, or 1 less than the number of successes. So I mean, the way I would kind of think this is 3 successes minus 1, right, or 2. And then the probability of failure, which is 5, 6, raised to, now let's just think about this. If there's 5 rounds of play, this one is always going to be 3. So 1 6 is always to the 3. And this one will always be y minus 3. So this one right here will be y minus 3. Sorry, I didn't leave much room for that. So y is the number of rounds of play. There are 3 successes, so there must be y minus 3 failures. Okay, well that looks like the generalization. The question mark we have now is what's the expected value of y? Which is, you know, that seems like a complicated question. So let's go to the calculator and see if we can get some intuition again like we did in the last example. So I'll just minimize this so we can come back to it. And let's go to the calculator again. I'm going to use a similar method, so I'll go to the statistics editor. I'll go ahead and put in here a sequence first of all. So let's go to list and bring in the sequence operator, number 5. So I need to do x comma x, which means the expression and what I'm evaluating in the expression, which is x and x. And I want it to run from 1 to, oh, let's let it go out to at least 100. And so that'll be, I guess, a list of the random variables. Oh, I just realized actually that that's incorrect, that I wouldn't want to include 3 in there, or 1 and 2, right? So let's go ahead and run that again, sorry. So let's go to ops sequence. We actually want it to be x comma x comma 3 comma, well, let's run it out to 103. Remember that the reason for that is the random variable in question, its domain is restricted to 3 to infinity. Okay, so now we'll go ahead and calculate the probability associated with each of those outcomes. Since we have an expression, we can put that expression in here. So the first thing is we are to take the value of the random variable here, which is L1, and subtract 1 from it, and take that number and combine it using combinatorics, combinations, L1 minus 1, choose 2. That's the first thing. And then what are we going to do? We're going to multiply that by 5, 6 raised to the, again, the value of the random variable, which is L1 minus 3. And then we're going to multiply that by 1/6 raised to the third. So just using the expression that we generated from our handwork to calculate the probability of each of these outcomes for the random variable. And you can see that as we sort of expected, that getting 3 right off the bat is actually not very likely, and actually in this case the probability is increasing, that the number of rounds of play are actually an increasing function of the random variable until we get to a certain value, and then what are they going to do? Then they're going to start to slope back down, it looks like. So this is sort of like a something that first rises and then decreases, and we could actually plot this if we wanted to, but I think I'll spare you that in this video. It just occurred to me that might be kind of fun to do. So we'll go ahead and now get a handle on the expected value by multiplying list 1 times list 2. So list 1 times list 2, get all the intermediate values for the expected value calculation, and then go ahead and get the cumulative sum of all of these values in list 3. Let's see, and in parentheses, hit an enter, and the big question mark here is there some finite value we're approaching? And you can see that things are increasing in the cumulative sum, still increasing. But now we're starting to slow down, and things are really slowing down now, and it appears that we are approaching 18 as a limit. And when we get out to the 103rd point, I guess at that point we've reached the machine accuracy of the TI 84 Plus Silver Edition, and indeed it's converging to 18 from there on out. So it seems like what's going on here, oops, I guess what I want is this, is that the expected value of y in this case is about, the question mark is 18. And again, this seems a little bit more than coincidence, because 18 happens to be kind of two important numbers, or has to do with two important numbers in the expected, I guess in the probability distribution itself. It has to do with the fact that we had 3 successes, and the probability of success is 1/6. So knowing that if we were counting just a single successful guess, and that would be 1 over p, it might stand to reason that in this case, if we were counting how many, I guess, how many rounds of play it's going to take for me to get 3 successful guesses, that I would take that 1 over p and multiply by 3, which would indeed give me 18. So the number of successes right here, and this would be the probability of a single success right here. So it does seem to kind of intuitively make sense that if, when you're guessing dice rolls, you think it's going to probably take 6 rounds of play on average to come up with that 1/6 probability of guessing right. And since we're accumulating 3 different rounds of play, it kind of stands to reason that, well, 3 times 6 rounds of play makes sense, because for one successful guess, we'd expect to play 6 times. So 18 rolls. This is a significantly longer game, right? Let's go ahead and talk about the theory then. Let's see, move this out of the way. So here's the theory behind the investigation, and it's this distribution that we call the negative binomial distribution. So we suppose that independent trials, so in a dice roll we're independent, right? So the game fits this description, each having a probability of success of p, and that fits the game as well. The probability of success was 1/6. And they were performed until a total of r successes is accumulated. So in our game contextualization, we were looking for 3 successes. If we let x equal the number of trials required, then the probability that x is equal to some value n is always n minus 1. Here, choose r minus 1. Probability of success raised to the r, that's the number of successes. In our case, that was 3. And then the probability of failure here raised to the number, I guess, of trials. Minus the number of successes, so that's how many failures you'll have. And notice that the support runs from r, the minimum number of successes that are required in the scenario, to countably infinite number. We say x then is a negative binomial random variable and has parameters, 2 parameters here, r and p, the number of successes and the probability of success. It turns out, and your book has a good proof that you might want to read about this, that the expected value of x, if it's a negative binomial random variable, it has an expected value of r over p, and that is, I guess, confirmed our result from numerics and the guess that we had. And it turns out also that the variance of x is r times 1 minus p over p squared. One thing you probably want to notice about these two values is that they're almost exactly the same as the geometric setting. The only thing is that we've added an r to both numerators. So if I scroll back here to the geometric one, you see 1 over p, 1 minus p over p squared. Fast forward to the negative binomial, we see r over p and r times 1 minus p over p squared. So in effect, we can take those values of a single success as expected value and variance and just simply scale them by r. For the negative binomial setting where we have more than a single success. So let's just conclude by applying the variance to our contextualized setting to get a sense of, well, how does that help us here understand the playing of this game? Well, we can say then that the variance of x is equal to r times, let me grab my notes here again, r times 1 minus p all over p squared. And in this case, that's going to be r is 3 successes, 1 minus p is, well, that's the probability of failure, that's 5/6, and p squared is going to be 1/6 squared. Okay, so it turns out that that's equal to, let's see, 15/6 all over 1 over 36, and what that ends up giving us is 6 times 15, which is 90, right? Okay, so 90 would be the variance of x. Let's take a look at what that means then for the standard deviation of x, which is the square root of 90. The standard deviation then is going to be somewhere in the neighborhood of 9.5-ish. And so what you should notice is that this variability is quite a bit higher. In fact, it's about twice as high as the variability that we got in the case where we only had one successful guess. If we wanted to kind of apply this to get a sense of like how many rounds of play are typical, so a typical number of rounds of play would be, well, we take the expected value, which is going to be 18, and we add and subtract the standard deviation to give a sense of the average distance from the mean, which is 18, and that leads us to I guess, well, it leads us to a sense of what a minimum 8.5 would be kind of a standard small game. And then let's see, 18 plus 9.5, 27.5 would be kind of a longer game, but still sort of within the realm of reason in terms of average variability. So average number of plays would be anywhere from sort of 9 to 28 rounds until you accumulate 3 successful guesses. If you were outside those bounds, you'd say you had either an extremely long game or an abnormally short game, a real rare short game. Okay, I hope that gives you a sense of this particular distribution. I'll go ahead and close here, and we'll take a look at the hypergeometric next.